09, 09, 09 equals 1 over 11. Okay, so 1/11 of x to the 11, and I've got 3 digits in between any two of these markers, is 0.90, 90, 90, etc. Okay, and then I'm going to add 5/6 of x to the 10. 5/6 is 0.8338. Oh, sorry, 8333.
Should be a half.
Oh! God, what am I? Oh. Oh no! A half, x to the 10, is a 5. There, is that right? Okay. Then we have x to the 9th, we have 5/6 x to the 9th, which is 0.83333, etc. I hope that's in the right position. Okay. And then what's the sum of those? Well, this 8 gets rounded up to 9, and then this becomes a 2 and a 4. I'll return to that in a little bit. 5 and 9 make a 4 and a 1. There's 9, 1. Okay. And now from here on, counting the numbers of adding so forth, I get 2, 4, 2, 4, 2, 4. And this will continue forever. And then what's the next thing I have to add? It's minus x to the 7th. Okay. Where's my correcting chalk? There's the x to the 7th term, and I've got to subtract 1 from it. I'll just change that 2 into a 1. Minus x to the 7th. 2, 4, 2, 4, 2, 4. Plus x to the 5th. Corrects that 2 to a 3. Now it's minus 5/6. Now, minus a half x cubed. So, 4, 2, 4, 2, 4, 2, minus a half at this level. I think I've got that wrong, haven't
It looks fine.
I? So minus 5 here.
Our computer will have finished by
Minus
now.
5.
Minus 5 in the next
next
digit.
one.
In which digit?
The next
Next
one.
digit's along.
Oh, after here. Oh,
Yeah.
that's it. So there was a 4, 2, 4, 2, 4, 2, etc. So we've got a minus 5 here. So that 2 and 4 get corrected to 1 and 9, subtracting 5 from 24. Two, 4, 2. 4, 2, 4. This is periodic with period 2. Those 2 4s carry on forever. And now what we have to do is we have to add, subtract, is it? No, add 5/6. 5/66 to the 1. Now 5/66 is 7.5/99, and so it's 0.07575. So that gets added here, 0.75. And now what do I do? 4 and then 2 full recurring, added to 7.5 recurring is 4 and then 9 recurring, but 9 recurring is 1. So this all gets rounded off to 5, 4, 4. Okay, so there it is. I don't know whether you get it. This sequence of digits here, 914099242441, 424243, 4242242425 north. This is some of the tens powers for the first 1,000 meters. I think at that point I just give up. Wait a moment. What is the time? I can't tell.
You beat Bernoulli's post so much.
My God. So, what was it? Did you time it?
It was about 8 minutes.
Sorry?
I got very close to 8 minutes.
Oh.
But I started sooner than I should have.
That's annoying.
Oh,
I always make little mistakes and need to be corrected about this. I have done it in about 6 minutes. But I was really hoping today to do it in less than 5, because then I could say intra-triente, quadram, quorum, inside a third of a quarter of an hour.
You can try again, you have 1 more minute.
Well, I don't know if it's worth it. Anyway, thank you. That's about it. Okay, perhaps I should say in regard to Bernoulli's boast, I'm not in competition with Bernoulli, because he was doing it for the first time, after all. At least I suspect he was doing it for the first time. Maybe it was the third time. And I have actually done this in front of an audience several times. That makes it both easier and harder, really. Harder because you've got to muster some words that help to explain what you're doing to an audience. Easier because I've done it many, many times now. Anyway, that's it. I will say, by the way, that since I've got a bit of time, that the Bernoulli numbers happen in the coefficients of the power series for quite a lot of functions. It's really not hard to see why, but I don't propose to actually see. If you take the standard trig functions, sine and cos, tan and cos, and sec and cosec, which I gather here you often abbreviate like that. For the sine and cosine, you really just use the factorial function to get the coefficients. For tan and cos, you use the Bernoulli numbers and the factorial function. For cosec, you also use the Bernoulli numbers and the factorial function. I'll show anyone how you get these if they actually want. And then for sec, oh dear me no. Sec needs the Euler numbers. Now, oh yes, I'll mention this triangle. It won't take very long, it really won't. If I can get up. This is a beautiful triangle discovered by a man called Andre. Start with a 1. Then underneath and to the left you write a 0, and then you add a move to the right, adding the number above the arrow. Now I put a 0 at the right hand end and move to the left, adding the number above the arrow. Then you stick it to the left again, add 1 and I get 1, add 1 and I get 2, add 0 and I get 2 again, so that's supposed to be a 2. 0 goes backwards to 2, backwards to 4, backwards to 5, stays at 5. 0, 5, 10, 14, 16, 0, and it will come out here at 61. Now, these are the numbers of zigzag permutations, or zigzag arrangements, I prefer to call them. A permutation, an arrangement of the numbers from 1 to n is, by combinatorists, often just called a permutation. I prefer to call it an arrangement. It's just some arrangement of the numbers from 1 to n in a line. It's a zigzag arrangement if they go alternately up and down. Let's write out the zigzag arrangements of 4 numbers. 1, 3, 2, 4, and 1, 4, 2, 3. And then 2, 3, 1, 4, and 2, 4, 1, 3. And then the last one, you can only just manage to do it. 3, 4, 1, 2. So there are 5 zigzag arrangements of 4 numbers, and that's the number 5 you can see here. Now the beautiful thing about this Andre table, or I call it the zigzag table, is that these numbers at the left are the coefficients in the power series for the secant function. 1 plus, with factorials, 1 plus x squared over 2 factorial plus 5x to the 4th over 4 factorial, and so on. Over here, with the odd powers of x over the relevant factorials, these are the coefficients of the tangent function. Absolutely beautiful fact, which deserves to be better known. But the coefficients of the tangent function are also expressible in terms of Bernoulli numbers, if you want them. But these things are totally different, and they're the Euler numbers. There are 2 things that once were both called the Euler numbers. Now somebody has decided that one of them should be called the Eulerian numbers. But I can never remember which is which. So I may have been giving them the Eulerian numbers by mistake. Okay, let's give up.
We have 4 minutes for questions, either about the dog or about John Conway's great life. Anybody has any questions?
Hello.
If you put minus x into this Sn, will you get the sum of from 0 to minus x of the
Essentially, I mean,
powers?
Up to little fiddles. I don't quite know what those little fiddles are. Incidentally, this raises, the Bernoulli numbers are also essentially the same as the sums of negative powers of the integers. That is to say, the zeta function, values of the zeta function. The values, it's rather funny. The value of zeta of 2n is a half of 2 pi b to the 2n over 2n factorial. I hope you understand what I mean by that. 2 pi b to the nth means, of course, 2 to the nth, pi to the nth, b to the nth, and then over the relevant factorial. The reason why it's a half is because the definition of the zeta function is not the most natural one. What happens really is, instead of summing over the positive integers, 1 over n to the s traditionally, you should sum over the non-zero integers. And then when you do that, if n is even, you're just getting the negative integers, and the positive integers give you the same thing, which is twice zeta of s. And that's why I told you to halve it, to get the one that is called zeta of s. If you sum over all the integers except 0 for an odd s, then you get 0, because the negative ones cancel the positive ones. And that's why the odd Bernoulli numbers are 0. Aha, not quite, except for s equals 1. But then what happens is, you see, either the sum over the positive integers or the sum over the negative integers gives you infinity, because it's divergent. And that's the way it gets out of the fact that B1 is not 0.
So infinity minus infinity is -1.
Yes, what actually happens is this. B1 takes two values. It's either plus a half or it's minus a half. And the average of those is 0. And anyway, it sort of manages to cheat its way around having to give a unique value. It's fascinating stuff, the Bernoulli numbers. They really are amazing. There's this wonderful theorem of von Staudt-Clausen, which is, it tells you what the fractional part of a Bernoulli number is exactly. Or in other words, it tells you what a Bernoulli number is mod 1. And the theorem is, you do the following thing. I'm only going to do it for even integers because of the fact that the other ones are 0. You take your number n. I shall take n equals 4. You write down the divisors of 4. You increase them by 1. And then you strike out any that aren't prime. Oh, well, I've done that. And so the answer is that B4 plus a half plus a third plus a fifth is an integer. It doesn't tell you which integer it is. Now let's do B8. B8, the divisors of 8 are 1, 2, 4, and 8. Increase them by 1, and then strike out any that aren't prime. Oh, so B8 is the same as B4 modulo 1. In fact, it's the same as B4. B4 and B8 are both minus 1/30th. If you take B12, B12 is a very interesting number. B12 is minus 691 over 2,730. Now, a theorem that I discovered recently, and then discovered it had been discovered a long time before, but I was prepared for that, actually, because it could have been proved at any time after von Staudt and Clausen independently proved their theorem. It's interesting, by the way. They both proved this theorem.
Sorry, John, let's finish the formal part of this talk.
Okay.
Back to stay for the informal part.
Okay, well, I won't say very much. Von Staudt-Clausen, I've been always very puzzled by the fact that they both proved this theorem independently in 1840. Von Staudt was a student of Gauss, and at the end of his paper, he has a Bemerkung, which says, a remark, which says, I've just been informed that in Schumacher's Astronomische Richtungen, last month or something like that, Thomas Clausen proves the same theorem as my recent one. Then he goes on to say, Hofrath Gauss will confirm that I told him this theorem some years ago. So anyway, it's usually called the von Staudt-Clausen theorem, although in respect of publication, it's the Clausen-von Staudt theorem. But I think we trust von Staudt.
And you already discovered it, so it should be called the Conway.
No, I didn't rediscover that theorem. I rediscovered the theorem that the fractional parts of the Bernoulli numbers repeat infinitely often, unless, with the single exception of a half. B14 is 1 1/6. B2, remember, was 1/6. Okay? B40 something is also an integer plus a sixth. I mentioned B12 minus 691 over 2,730. B24 is minus 5, 8. I've lost this. Does my keeper remember that integer?
No.
No.
My computer remembers.
Anyway, it's minus a 5-digit number and 691 over 2,730. That's the repetition theorem. It's a trivial, almost trivial consequence of the von Staudt-Clausen theorem. So I guessed, since it's been a long time since 1840, that anybody could have proved it after 1840. And then we found, in fact, that Erdős and Wagstaff proved it, I don't know, 25 years ago or something. And they proved a stronger version of the theorem, which I don't think I'll explain because I'm not sure I can get it right. But it's absolutely amazing. The graph of the fractional part, there is a graph of the fractional parts of the Bernoulli theorem, of the Bernoulli numbers. And it's really wonderful. The Bernoulli numbers don't give up on you. They keep on saying, new things, new and highly interesting things.
Okay, thank you very much for that.